In this section we will look at low voltage systems. These are used in all situations, from the electrical system in your house to complex industrial networks. So you need to understand all of the basic principles of how they operate and how to use them safely. I hope you enjoy the section. The aims of the course today are to show the basic features of low voltage systems, to look at a basic socket ring system, to show the different lighting circuits that are used, let's look at a typical house and its electrical system. Firstly, we have the main supply from the local distribution system. This feeds the power into the house and is terminated on the consumer unit. We then have lighting loads in each room of the house. Most houses have a cooker in the kitchen, fed directly from the consumer unit, as it draws a substantial amount of current. And finally, multiple sockets spread around the house. Firstly, let's look inside a typical consumer unit. The first thing we have is incomer circuit breakers to turn on and off the supply from outside the house. These are usually red in colour and switch on and off the live and neutral systems. Feeder circuit breakers to turn on and off the lighting, socket and other circuits. These normally switch the live feed only. A neutral terminal strip to terminate all of the neutral wires. And finally, a ground terminal strip to terminate all of the ground wires. You will find all of these basic elements in any house consumer unit. Let's look at how we wire the individual elements. Firstly, we have the incomer cable, carrying the electrical supply into the house. This connects to the incomer circuit breaker, which switches both the live and neutral wires. The ground wire does not need to be switched and is connected straight to the ground terminal strip. The neutral terminal is now connected to the output of the incomer circuit breaker. Next we need some feeder circuit breakers for feeding the electricity around the house. These are all connected to the incomer circuit breaker via the live busbar. To connect a feeder cable, we simply connect the ground and neutral to their terminal strips. And finally, a live connection to the feeder circuit breaker chosen for that circuit. We normally only switch the live connection for feeders. Here's how we connect the electrical sockets to the consumer unit. Here we have the consumer unit as before, with some feeder circuit breakers, a neutral terminal strip, a ground terminal strip and a live bus bar. Here we have a single socket. This is a 3-pin socket with a live, neutral and ground. Firstly, we connect the live feed from the circuit breaker through the cable onto the socket. Then we connect a neutral feed from the neutral terminal strip through the cable and onto the socket. And finally, we connect the ground wire from the ground terminal strip through the cable and onto the socket. We normally group the sockets together into one circuit, fed from the same feeder circuit breaker. Let's see how that's done. Here's our consumer unit from before, with a live bus bar, a feeder circuit breaker, a ground terminal strip and a neutral terminal strip. As before, we have a live connection from the feeder circuit breaker onto the socket, and a connection from the ground terminal strip to the socket and the neutral terminal strip to the socket. Here we have another socket. This is connected in parallel to the original socket. All we need to do is loop the ground wires across, the live wires across, and the neutral wires across. We can keep on adding as many sockets as we need. This is a standard radial socket circuit. To turn a radial socket circuit into a ring socket circuit, we simply loop back the live, neutral and ground wires to the consumer unit. We now have a ring system, with power flowing into the loop from both directions at the same time. Most domestic socket circuits are connected in a ring system, as this reduces any volt drop issues and shares the current better around the circuit. Let's now look at a standard lighting circuit. Here we have our consumer unit from before. Firstly, we have a light bulb with a live, neutral and ground connection. We have a single pole light switch with 2 connections. We connect a live wire from the feeder breaker to the single pole light switch. We then connect the live of the light switch to the light bulb. And finally, we take the neutral back to the neutral terminal strip and the ground back to the ground terminal strip. By closing the light switch, we apply the live to the light bulb and it turns on. By opening the light switch, we remove the live from the light bulb and the light bulb switches off. The main thing to remember is always switch the live connection and not the neutral. Here we have a typical ceiling rose. Inside the ceiling rose we have a neutral terminal strip, a live terminal strip, a switch terminal strip and a ground terminal strip. The light bulb hangs down from the ceiling rose and is connected to the neutral terminal strip, the ground terminal strip and the switch terminal strip. Firstly, we need to connect the supply to the ceiling rose. As this is a ring, it comes in from two separate directions. We have a cable from the left-hand side of the ring. From this we connect the live to the live terminal strip, the neutral to the neutral terminal strip, and the ground to the ground terminal strip. We then connect the right-hand ring. We have now energized the ceiling rose. We have a separate light switch, which is normally on the wall. Firstly, we connect a live connection to the switch, from the live terminal in the ceiling rose, through the cable, and onto one side of the switch. Then we take the live connection back, through the cable, and onto the switch terminal strip. And we connect the ground wire to the ground terminal strip. To signify that the black wire is really a live wire, we put a small red marker on both ends. This is a common way of wiring lighting ceiling roses. Another common lighting circuit is for the stairwell or corridor, where one light is controlled from two light switches. Firstly, we have a light bulb. Here we have two two-pole light switches, one at the bottom of the stairs and one at the top of the stairs. They are called two-pole light switches because they have two possible output conditions. We then connect a live to one side of the switches and a neutral to the other side of the switches. The common point of the switch connects to the light bulb. This arrangement relies on the fact that a bulb will only light up if we apply a live and neutral to it. Which way we apply the live and neutral doesn't matter. By operating the left-hand switch, we change the supply from live to neutral. We now have neutral and live across the light bulb. It therefore lights up. By operating the right-hand switch, we change the supply from live to neutral. We now have neutral on both sides of the light bulb. It therefore doesn't light. Whichever switch we operate will change the status of the light bulb, from off to on, or on to off. Let's now summarise what we've learned today. The power to a house is fed in through a consumer unit, which contains an incomer circuit breaker, feeder circuit breakers, a neutral terminal strip, and a ground terminal strip. The socket circuits in a house are fed in a ring system to limit the voltage drop. The lighting circuits are also fed in a ring system, with two double pole switches used. In this section we will look at electrical cables. These are used throughout the electrical power network, from carrying low voltage signals to control the equipment, right up to the power cables that carry high voltages and currents around the network. Understanding how they operate and their limitations is essential to the operation of the network, so please take time to understand the principles shown. The aims of the course today are to show how electrical cables are constructed, show how cables are sized based on the current, length and volt drop, to show how power cables are installed. Cables are used to take the electricity from the source to the load. They range from simple 2-core 240-volt cables in domestic situations, right up to single-core 275,000-volt cables for transmission systems. They tend to all have the same basic design features. Here we have a typical single-phase distribution power cable. Let's look at the different layers. Firstly, we have a conductor to carry the electricity through the cable. This is usually made of a low-resistance material such as copper or aluminium. The diameter of the conductor depends on the current flowing through the cable. As the current level increases, the diameter of the conductor also has to increase. If we made the conductor from a solid piece of metal, it would be inflexible and difficult to bend round corners, so it is usually made from multiple strands of material bound together. An insulating layer to stop the electricity leaking out. This is usually made from a high-resistance material, such as plastic or rubber. The thickness of the insulating layer depends on the dielectric strength of the material and the voltage level of the electrical supply. As the voltage level increases, the thickness of the insulation layer also has to increase. A waterproof layer to protect the cable and stop water getting inside it. The waterproof layer is usually made of rubber or plastic. A layer of armour to protect the cable against external damage. Armour only tends to be provided on cables that are directly buried in the ground, or in an area where the cables are likely to be susceptible to damage. An external jacket, which provides physical protection for the cable and is embossed with the cable manufacturer, size, voltage rating and current rating. Distribution and transmission cables tend to be one of the following types. Here is a typical 4-core power distribution cable. 4-core cables are used on low or medium voltage 3-phase circuits and consist of red, yellow, blue and neutral conductors. They are a cost-efficient way of carrying 3-phase power. They are limited to lower current ratings, as when very high currents are required, the conductor size is increased to a point where the cable becomes too bulky. The arrangement of the cable conductors minimises the electrical losses, as all 3 individual phase electric fields partially cancel each other out. Here is a typical 3-core power distribution cable. 3-core cables are used on medium or high voltage 3-phase circuits, consist of red, yellow and blue conductors. They are limited to lower current ratings, as when very high currents are required, the conductor size is increased to a point where the cable becomes too bulky. The arrangement of the cable conductors minimises the electrical losses, as all 3 individual phase electric fields partially cancel each other out. And finally, we have a single core power cable. single core cables are used for high current applications. They are the most expensive way of transmitting the power from the source to the load. When used in a three-phase circuit, the losses can be high, unless the cables are arranged in a trefoil arrangement. Here we have a typical trefoil arrangement with three single-core power distribution cables. The cables are spaced equal distances apart. The angle between the cables is 60 degrees. Because of this arrangement, some of the red, yellow, and blue electric fields cancel each other out, reducing the losses on the cable. To select which cable we want to use, we need to look at the data tables from the cable manufacturer. Here we have a typical cable data table. The table shows the cross-sectional area in millimeters squared, the maximum continuous current carrying capacity in amps, and the resistance per meter in ohms. We can see that as the cable cross-sectional area or size increases, the resistance per meter decreases. As the cable cross-sectional area or size increases, the current carrying capacity increases. We can use this data together with the system parameters to work out which cable we need to select for any application. Let's do a worked example. For a circuit that will carry 128 amps continuously, choose the correct cable. Here we have the table from before. All we need to do is go down the table and select a cable that can carry the current required. From the table we can see that 50 square millimeter cable is suitable, so that's the one to go for. We always choose a cable that can carry more than the required load, so we could in theory choose a 70 square millimeter cable as well. We can see from the table that each cable also has a resistance per meter. Let's call it RC. This is a linear relationship, so as the cable gets longer, its total resistance increases by the same amount. Therefore, for a cable 3 times longer, the resistance will be 3 times higher. Let's now look at a typical circuit. Here we have a standard circuit with a live, a neutral, and a load, with current flowing and voltage V source at the input. In this ideal condition, the voltage at the load, V load, equals the voltage at the source, V source. In practice, we need to consider the resistance of the cables that carry the electricity from the source to the load, RC. The cable carries current and has a resistance, therefore it must generate a voltage across it from Ohm's law. This results in the voltage at the load, V load, being less than the voltage at the source, V source. This difference is called the cable volt drop. Let's do a worked example. Using the data table, select a 250 meter long cable that can carry 92 amps and keep the cable volt drop below 10% of the source voltage of 230 volts. Step 1 is to select a cable from the table based on its current carrying capacity. Here's the cable data table from before. Looking at the table, a 25 square millimeter cable can carry 92 amps. Let's choose that one. Step 2 is to calculate the cable volt drop. From Ohm's law, voltage equals current times by resistance. Resistance equals cable length times by the cable resistance per meter. Here's the cable data table from before. We can see from the table that for our 25 square millimeter cable, the resistance per meter is 0.000727 ohms per meter. Let's put that into the equation. Resistance equals 250 meters, which is the cable length, multiplied by 0.000727 ohm meters from the cable table, equals 0.181 ohms. Therefore, volt drop equals 92 amps, which is the cable current, multiplied by 0.181 ohms from above, equals 16.65 volts. This means that the voltage at the end of the cable will be 16.65 volts less than the voltage at the start of the cable. Step 3 is to calculate the volt drop percentage. Percentage equals 16.65 volts from the equation above, divided by 230 volts, which is the source voltage, equals 7%. Therefore, a 25 square millimeter cable is okay. What would we have done if the volt drop had been above 10%? Well, the next course of action is to choose the next size cable up, which is 35 square millimeter. This has a lower resistance than the 25 square millimeter cable, so the volt drop would have been lower. If we do the calculation and it still isn't okay, then we would keep on doing the calculation on the next cable size up until the volt drop falls within the 10% level. Most of the distribution and transmission cables that we install are buried in trenches underground. Let's see how that's done. The first thing we do is dig a trench that's deep enough and wide enough for the cable arrangement. Here we've dug it 1.2 meters square. The first layer we put down is 0.2 meters of thermally suitable sieved fine sand without sharp objects. We take out the sharp objects so they don't damage the cable. Cables generate a lot of waste heat. We therefore put a layer of thermally suitable sand to absorb the heat. In this situation we've got 3 single core cables, so we're going to do a trefoil arrangement. The first stage is to put 2 single core cables at the lower level. We then have another layer of thermally suitable sand. Next we have the remaining single core cable. Then we have a final layer of sand. The cables are spaced equal distances apart. The angle between the cables is 60 degrees. A trefoil arrangement. Above the sand we have some concrete tiles. The concrete tiles give a physical barrier to protect the cable. They are normally marked with danger, electricity. We then have a layer of dirt, followed by a layer of warning tape. The warning tape gives the first indication that there's cables below. The warning tape is either plastic warning tape or a board. Finally, we have a layer of dirt to bring it back up to the surface level. Every layer in the trench is important and is installed for a reason. If someone does accidentally dig into the ground, the first thing they will hit will be the warning tape, which should hopefully make them stop digging. If this doesn't work, then they will hit the concrete tiles, which are the real physical barrier before they get to the power cable. Let's summarise what we've learned today. Cables consist of a low resistance conductor to carry the current, an insulation layer to stop the electricity leaking out, and additional outer layers to protect it. The size of the cable is chosen based on the current and voltage it carries, and the acceptable volt drop along it. When a power cable is installed in a trench, it is surrounded by thermally suitable graded sand and protected by cable tiles and warning tape. In this section we will look at overhead lines. These are the workhorse of the distribution and transmission systems and carry bulk power around the network, from the generating stations through to the end user. By the end of this section you will understand the different types of overhead lines that we use, why they are shaped as they are, and know all of the basic elements that go into their construction. The aims of the course today are to show the basic principles behind overhead line design and construction, to introduce the different overhead line tower types, to look at the different conductor types and how they compare, overhead lines are used to take electricity from where it is created to where it will be used, usually over substantial distances. The size and shape of the overhead line used depends on the voltage level. As we've seen from previous sections, electricity can jump through the air. As the voltage of the circuit increases, so does the distance that the conductors need to be from the ground and from each other. Transmission level overhead lines carry three-phase conductors: red, yellow and blue. Distribution level overhead lines can also carry a neutral conductor. The type of the overhead line depends on the voltage level, but they all consist of the following basic elements: a wooden or steel post structure to lift the live conductors off the ground and to keep everyone a defined distance away from them. A set of insulators to separate the live conductor from the grounded pole. These are usually made from a good insulator, such as ceramic, glass or plastic. The live electrical conductors themselves and the accessories to fix them to the top of the insulator. The conductors are usually made from copper or aluminium, as they are good conductors of electricity and are reasonably low cost. We need to take into account the following distances when we design an overhead line. The phase-to-phase clearance between the red, yellow and blue electrical phases. the distance from the live conductors and fixings to the supporting structure or pole. The safety distance from the live conductor to the ground to protect members of the public. We also need to take into account the conductor sag. The conductors are made of metal. When current passes through them, they get hot, expand, and the conductor sags closer to the ground. When we look at the clearance to the ground, we also need to look at the terrain, whether any trees are growing nearby, and the location of any buildings and roads. When we are looking at the conductor sag, we have to assume the worst possible conditions, which includes the highest ambient temperature for the location and the maximum conductor current. We then add a factor of safety to take into account possible material differences and the components aging. We then look at the terrain over which the line will cross. If this includes a roadway, we need to consider Department of Transport requirements for the size of vehicles. Let's see how we design a transmission level tower. First thing we have is piled foundations on each of the leg. These can be up to 25 meters deep for the larger transmission towers. We then have the aluminium lattice tower. Aluminium is used as it's light and strong and resistant to corrosion. The tower has to be designed to deal with all the loads imposed on it. This includes the environmental factors, snow, ice and wind, and also the weight of the conductors and the tensional loads imposed by the conductors. The structure is grounded to protect from lightning strikes or accidental touching by the live conductor. Let's add some insulators to stop the live conductors touching the grounded steel tower. We normally have two independent circuits, one on each side of the tower. We have red phase conductor, a yellow phase conductor, and a blue phase conductor. The first electrical clearance distance is to prevent the live conductor arcing across to the grounded structure. The second electrical clearance distance is to prevent the live conductor arcing across to the other live conductors. The third, larger electrical clearance distance is to prevent the live conductor arcing to objects on the ground. This is why, as the conductor voltage increases, the tower gets taller, as it needs to position the conductors farther away from the ground. Let's look at transmission tower insulators in more detail. Each insulator segment is designed to withstand a fixed voltage level. The insulator is shaped to maximise the distance around the edge. This stops the electricity tracking around the outside of the insulator. By stacking the segments in series, a higher voltage withstand can be achieved. Here we have a single insulator, but a voltage withstand of 10 kV. By stacking the insulators in series, we can get an overall voltage withstand level of 50 kV. There are two common ways of keeping the live conductors away from the grounded steel tower. The first method is to hang the conductor on insulators beneath the tower arms. These are called suspension insulators. They are designed to carry the weight of the conductors and any loads applied by the environment, either wind or snow. The second method is to use the insulators to connect the conductor horizontally. These are called tension insulators. These are designed to carry the conductors under tension in addition to carrying any loads applied by the environment. The conductor is strung underneath the insulators to maintain the circuit. We tend to see two common types of towers for transmission systems. The first group has different names including through, straight or inline towers, but they are all essentially the same. This type of tower is used when we have long straight runs in the same direction. Because the loads from the conductors and insulators on each side of the tower are balanced, the tower design can be quite simple and the amount of steelwork kept to a minimum. The towers are typically spaced about 250 meters apart. With towers of this type, we can normally allow a 15-degree change in the overall direction of the towers, as this has minimal impact on the loadings. The second type of towers are used when we need to change the direction or height. These towers are generally known as modular or strain towers. Because the loads on each side of the tower are no longer balanced, the towers need to be stronger and have additional steelwork. Each tower is unique and designed for the specific loads imposed on it. To achieve the required current carrying capacity, the overhead line conductor consists of multiple uninsulated conductors bound together. To get the required cross-sectional area, we can have a large amount of small conductor strands or smaller amounts of larger conductor strands. By changing the type and quantity of the individual conductor strands, we change the following: the conductor current carrying capacity, the physical strength and weight of the conductor and how much it sags when it gets hot, the resistance and impedance of the conductor and how much energy is lost as current passes through it. Conductor types are therefore chosen carefully to meet all of the above criteria. There are many possible combinations of the number of strands and conductor sizes. To simplify things, there are international standards that give the different conductor types unique names. These tend to be based around types of animals, birds, insects, or vegetables or fruit. Here are some examples. From British Standard 215 Part 1 for aluminium conductors. This standard uses the name of insets for the different conductor types. The number and diameter of the strands is different for each conductor. This affects all of the conductor characteristics, such as the overall conductor diameter, weight, breaking load, DC resistance, and current rating. For American ASTM B231-B for aluminium conductors, we can see that this standard uses the names of flowers for the different types of conductors. Again, each of the conductors is different and has different characteristics. These are just a couple of samples of the hundreds of combinations available. Most electrical utilities will choose a single conductor type for each of their system voltage levels, which covers all of their system needs. This avoids the necessity of storing lots of different conductor types, which would be wasteful. Let's now summarize what we've learned today. The size and shape of the overhead line that we select for a particular use depends on the voltage level and where it is to be located. When designing an overhead line, we need to take into account the electrical clearances. We need to select the conductor to be used from the standard types, based on the current carrying capacity, sag requirements and loss parameters. Congratulations for making it to the final section of this course, which looks at the design and operation of transformers. Transformers are an essential part of the network and allow it to operate efficiently and safely. By the end of this section, you will understand why we need them and how they operate. The aims of the course today are to show what a transformer is and how it operates, to introduce the basic transformer equations, to show how a transformer can be used in specialized situations, here we have a standard coil. Here we have a coil fed from an AC source and controlled by a switch. When we close the switch, current flows through the coil and the coil becomes magnetized with an alternating magnetic field. Now let's see what happens when we bring another coil into its magnetic field. A voltage will be induced onto coil B as the lines of alternating magnetism are cut. If a circuit is now connected to coil B, a current will flow in it, and electrical energy will be transferred from coil A to coil B. This arrangement is called a transformer. So here we have a transformer with winding A and winding B. Winding A has voltage A and current A. Winding B has voltage B and current B. Note that the current in winding B is in the opposite direction to the one in winding A. If we want to improve the magnetic link between the windings, we can add an iron ring that passes through them both to form a continuous magnetic path. This is called a magnetic core. We call the number of times the wires are looped around the core the number of turns. So for the above example, both windings A and B have 15 turns each. Let's look at some of the characteristics of a transformer. if windings A and B have the same number of turns, winding A voltage VA equals winding B voltage VB. Winding A current IA equals winding B current IB. Winding A power in equals winding B power out. If we now make it so that winding B has half the turns of winding A, then winding A voltage VA equals twice winding B voltage VB. Winding A current IA is now half winding B current IB. Because the power is the summation of the voltage and the current, winding A power in still equals winding B power out. Therefore, we have changed the output voltage and current by changing the number of turns on each winding. Even though the ratio of the input and output voltages and currents has changed, the power flow through the transformer has stayed the same. By knowing the precise number of turns in each winding, we can work out the transformer turns ratio, which establishes the ratio of the currents and voltages. Transformer turns ratio equals the number of turns on winding A divided by the number of turns on winding B equals NA divided by NB. The voltage ratio equals the voltage on winding A divided by the voltage on winding B equals the transformer turns ratio NA over NB. The current ratio equals the current in winding A divided by the current in winding B equals the inverse of the transformer turns ratio, NB over NA. Let's do a worked example. For the transformer shown, what is the value of VB and IB? From the previous slide, transformer turns ratio equals NA over NB. From above, this equals 1000, which is NA, divided by 10, which is NB. This equals 100. Therefore, VA over VB equals the transformer turns ratio equals 100. Therefore, VB equals 230, which is the voltage on winding A, divided by the turns ratio, which is 100. Therefore, VB equals 2.3 volts. The current ratio is the inverse of this. So therefore, the current ratio equals NB over NA. Equals 10 divided by 1000. Equals 0.01. Therefore, IA over IB equals 0.01. IB equals 10, which is the current on winding A, divided by 0.01. Therefore, IB equals 1000 amps. We can see from the above that the voltage on winding B is now 1/100th of the voltage on winding A. The current on winding B is 100 times the current on winding A. But remember, the power will remain the same on both windings. The power rating of the transformer is the maximum amount of energy that can continuously pass from winding A to winding B, or vice versa. Here we have the transformer from before. Here we have VA max, which is the maximum rated voltage for winding A, and IA max, which is the maximum rated current for winding A. On winding B, we have VB max, which is the maximum rated voltage for winding B, and IB max, which is the maximum rated current for winding B. The transformer power rating equals the maximum rated voltage on winding A multiplied by the maximum rated current on winding A, or the maximum rated voltage on winding B multiplied by the maximum rated current on winding B. The transformer power rating is measured in VAs. Note that for the transformer rating, we do not consider any power factor. When we are dealing with transformers, we usually call winding A the source winding, the primary winding, and winding B, the load winding, the secondary winding. So here we have the transformer from before. On the primary winding, we have the primary current IP and primary voltage VP. On the secondary winding, we have the secondary current IS and secondary voltage VS. We have to be very careful with transformers, as very large currents and voltages can be created. For example, imagine a transformer with 1 turn on the primary and 10,000 turns on the secondary. This would result in the voltage on the secondary winding terminals being 10,000 times higher than the primary input voltage, which could be very hazardous. Let's look at one way we can use this high ratio effect to good use. If we place a high turns winding around a conductor carrying current, the electric field of that conductor would induce a small representative current in the winding. This device is called a current transformer, or CT, and is used for measuring purposes. The value of the current ICT will depend on the number of turns on the current transformer. With ICT equaling the current flowing through the conductor divided by the number of turns on the CT. Let's do a worked example. Calculate the value of the secondary current ICT. From the previous slide, ICT equals the current flowing through the conductor divided by the turns ratio. From above, this equals 1600 amps divided by 900 equals 1.77 amps. The CT current is a direct representation of the main conductor current. CTs are used widely in electrical systems to monitor the main currents, ensuring that the system is healthy. Let's summarise what we've learned today. If two windings are brought close together and one is energised with AC, then a voltage will be induced from one to the other. If we connect a circuit, current will flow in the second winding and power will be transferred from the first winding to the next. This arrangement is called a transformer. We can alter the value of the voltages and currents that are induced in the second winding by altering the turns ratio. We call the source winding the primary winding and the load winding the secondary winding. We can create a current transformer that can accurately measure the current in a conductor.